Hello students, welcome to the physics class on solid state physics, which comes under your paper 6A of your semester 5. Now let us go into unit 4. I am N. Chandana, assistant professor of physics from Government Degree College, Khartabad. So let me share a whiteboard now to explain the superconductivity, the phenomenon. Today we are going to learn superconductivity. Okay. What is superconductor? Okay. Superconductor. Superconductivity. It's the phenomena. The conductor which exhibits this phenomenon, superconductivity, is called superconductor. Superconductor. You already know what is a conductor, right? A conductor means electrical conductor exclusively, which allows the current to pass through it, right? Which allows the current to pass through it. That is less resistance. It has less resistance and more conductivity. While when we come to insulator, we have more resistance and less conductance or less conductivity. More resistivity and less conductivity, less resistance and more conductivity. So insulators, electrically insulators means we have a wooden block, right? It is an electrically insulator. What is an electrical conductor? For example, we have copper. We have copper wires. They are electrical conductors, copper rods, iron rods. Okay. Now we have insulators, wooden block, and copper rods. They comes under copper wires. They comes under conductors. Okay, for electricity to pass through them. Now, in between this resistance, like the materials which have more resistance than that of the conductors and less resistance than that of the insulators are called semiconductors, right? Semiconductors. Okay, students, semiconductors. Now we are dealing superconductivity, superconductors. So what is a superconductor? Let us go now. So superconductor means we always see, like Superman, means they have extreme power, like they are unresistible. They don't have any negativity, no weak points. They are unresistible. Okay, so no one can resist them, no one can oppose them. Okay, that means there is zero resistance. Zero resistance. No one is able to stop them. They have zero resistance. They have zero resistance. So superconductors have zero resistance. Okay, so this was given by Camerling-Owens. Okay, this was given by Camerling-Owens. I have explained you in your third sem, in your thermodynamics, low temperature physics. I have explained you this superconducting material, low temperatures, and you know Camerling-Owens there. Okay, so Camerling-Owens in 1911, he has given the first phenomenon of superconductivity. Okay, so Camerling-Owens is the one who has discovered the phenomenon of superconductivity in 1911. Okay, how did he do? While he was measuring the resistivity of mercury, he was measuring the resistivity of mercury, Hg, mercury of resistance of mercury at extremely low temperatures. He was measuring low temperatures. He was measuring. That's the reason we have learned this in your third semester. And I am dealing about low temperature physics. I have told you. Again, let us see. While measuring the resistivity of mercury at low temperatures, he suddenly observed that the electrical resistivity of pure mercury suddenly drops to 0 at temperature 4.2 Kelvin. He has observed this at 4.2 Kelvin. Okay, so this is, so what does it mean that the resistance, there is no resistance? That means there is zero resistance for the material, that is mercury here. So now the mercury behaves as superconductor at what temperature, ma? At 4.2 Kelvin, and more than 4.2 Kelvin, it is again a normal mercury. But when the temperatures, this mercury, this temperature 4.2 Kelvin is called, what is that called? Critical temperature. Okay, this is called critical temperature. Okay, ma? This temperature is called critical temperature. Okay. Now for mercury it is 4.2 Kelvin. This is called critical temperature. Okay. Now let us have a definition, clear cut definition. Now I'll draw here. So what we can say, when a substance loses, right? Loses its what, ma? Electrical resistance. I told you electrical conductivity, electrical resistivity. So electrical resistance completely. Okay. That means there is no change in current when passing through it. There is no reduction of current when it is passed through it. Then this phenomena is called superconductivity. Superconductivity. Okay. Also in the other way, when the electrical resistance of a substance drops to 0, then this phenomena is called superconductivity. Okay, superconductivity. Here I have written superconductivity. Okay, then below certain temperature, at a particular temperature called Tc, the resistance become 0. Resistance is becoming 0. Okay, now less than these temperatures also we have the same conducting state, that is superconducting state. And above Tc, again the substance behaves as, above Tc the substance behaves as normal state. It has its own normal state. Below that temperatures and at the temperature, critical temperature Tc, the resistance becomes 0. Hence it exhibits superconducting state. Superconducting state. Okay, students? Superconducting state. Okay. For example, we have for aluminium also exhibits superconducting state, but at what temperature? 1.19 Kelvin. Okay. Similarly, for mercury, we have already seen. Now, even for cadmium, tungsten also exhibits, but very low temperature, 0.01 Kelvin. This is the critical temperature. Below these temperatures, we have tungsten behaving as a superconducting material. Okay. Now, next we go for some basic experimental facts of superconducting materials. Now, understood what is a superconducting material? Now let us go for some basic experimental facts. Experimental facts means after doing some experiments repeatedly, then the scientists have come up to some conclusions, which are known as experimental facts. Okay, they're proved about what basic experimental facts of what about superconducting materials or superconducting substances. Okay, about these materials, let us see what are the basic experimental facts we have. See, at room temperature, you will be surprised to see the experimental facts. At room temperature, superconducting materials, superconducting materials have more resistivity, you know that? Have more resistivity than other elements. But when we approach to critical temperature less than Tc or equal to Tc, then what happens? The resistivity suddenly drops to 0. Then it becomes superconducting material. But in general, the superconducting materials, they are in normal state, they have more resistivity. They have more resistivity than that of the normal other elements. Okay. And also, you know the isotopes. We have isotopes, right? Isotopes means you have same atomic number but different mass number. Here, for isotopes of different elements, okay, the transition temperatures will vary. Tc will vary. You may think that for one element, the critical temperature will be the same. No, based on the isotopes. If for different isotopes of the same element, we have different Tc. Okay, will vary. And also you can observe that it decreases with increasing in atomic weight. It decreases. So Tc will be more for first isotope. Like if 1H1, 1H2, 1H3. These are the isotopes of hydrogen, right? Tritium, deuterium, and hydrogen. So what happens now? When atomic weight is increased, the critical temperature will be less. This is less than this, than this. Okay. So this is the way we can explain the critical temperature. The critical temperature varies with respect to the isotopes of the elements. It is not constant for a single element. Similarly, the superconducting property is not lost here. See here, the superconducting property is not lost by adding impurities. Okay, by adding impurities. By adding impurities. I'll clear the board. So first point, what did I tell? Superconducting materials have high resistivity than normal materials or elements in normal state. But once we go to the critical temperature or less than the critical temperature, they exhibit superconductivity property, that is resistivity will become 0, right? That is the first point I have explained. What is the second point? We have to know that the isotopes have different TCs, different critical temperatures, and critical temperature decrease will decrease with respect to atomic weight. Okay, increase in atomic weight. Now, third point I'm going to talk about is when we add impurities. When we add impurities to the superconducting material, superconducting element, then what happens is there is no change in the superconducting nature. Okay, superconducting nature is not lost. But once you add some to mercury, if you add some impurities, the superconducting nature of mercury will never lose. It is Hg. Mercury it never lost, but the critical temperature will vary. Okay, you have to remember that the critical temperature will be varied. The critical temperature may be lowered. That means the critical temperature Tc will be lowered. Okay, will be decreased. Okay, when we add impurities, when we go on increasing impurities, the critical temperature will be getting lowest and lowest. If for at normal state at 4.2 Kelvin you are achieving for mercury superconducting state, but when you add upon impurities to mercury, then it may be reduced to 3.8 Kelvin based on your impurity content. Okay, if you add more and more impurities, it may go to 3 Kelvin sometimes. It may go to 2 Kelvin also. That means by adding on impurities to the superconducting element, the critical temperatures will be lowered. Okay, but there won't be any change in the superconducting state of the system. Like the element will exhibit superconductivity property, but the critical temperature will be lowered. Okay, so these 3 points you have to remember. These are the basic experimental facts. This may come as a short answer question, and also it's a very interesting facts, right? To do some experiments on superconductors. Okay, and also by XRD, already I have told you why you do XRD, X-ray diffraction. Okay, to determine the crystal structure. X-ray diffraction, they have determined that there is no change in the crystal structure. There is no change in the crystal structure when the substance is changed from a normal state to superconducting state. Okay, so when a substance is changed from a normal state to superconducting state, there is no change in a crystal structure. There is no change in crystal structure. This has been also observed. Okay, now they also observed that the thermal properties. Okay, in thermodynamics we have learned thermal properties like entropy is and heat capacity and also thermal conductivity. Thermal conductivity we have learned in your third semester. Conductivity, okay, of a metal, of a metal, okay, of a metal change, okay, sharply at transition temperature. Change sharply at the transition temperature. That means at TC, the properties like entropy, thermal properties, heat capacity, thermal conductivity of metals, they sharply change at this transition temperature or critical temperature. Okay, they have observed that the thermal conductivity will decrease. That the thermal conductivity will decrease. Thermal conductivity will decrease when that superconducting state is reached. Okay, decreases. The thermal conductivity decreases when we reach to the superconducting state. When our metal reaches to superconducting state, the thermal conductivity of the metal, originally it would be some value, no? Thermal conductivity is denoted by K. So K is equal to MST alpha by R plus D into R plus D by R plus 2D into 2 pi R square. You have learned this, right? In your second year thermal conductivity of a bad conductor when you are going for practical. Okay, so there we have learned this. So thermal conductivity value, if it is originally in some value, that get decreased less than K when it is K1 for normal state, but when it is in superconducting state, the metal, then it gets decreased. Okay, this is one of the phenomena. So the entropy and the heat capacity and thermal conductivity of metal changes when the metal, originally it is metal in some form, when it gets transformed into superconducting material, then automatically these all thermal properties will come into changes. Okay, but they have observed that the elastic properties doesn't change. The elastic properties won't change. The elastic properties won't change. Coefficient of elasticity, they won't change with respect to what? With respect to this superconducting states. Okay, and also the thermoelectric effects. The thermoelectric effects disappear in superconducting state. Thermoelectric effects disappear in superconducting states. Okay, so now thermoelectric effect disappear in superconducting state and the elastic properties cannot be changed in the superconducting state. Okay, now all these 6 properties you have to understand. These are the facts. They are not properties exactly. They are the facts observed while they have conducted so many experiments on superconducting materials. They were shifted from normal to uh, superconducting state. Okay, so when they ask you an exam, you have to list out them 1, 2, 3, 4, 5, 6, 7. What all I told, to list out them 7, and you explain why this happens. See, these things happen and they're very interesting to learn the superconducting materials. Okay, now explanation of superconductivity and zero resistance I'm going to do. So superconductivity linked to zero resistance. Why it is happening? Why it is happening? Let us see. See, see what is happening is the electric resistance of ordinary material. Why ordinary material is due to what reason? Ordinary material or metals, for metals exclusively. Why do we get electrical resistance? Ma? Why do we get resistance? Because Electrical resistance is due to collision of electrons. So collision of electrons. So these electrons will collide in the metals with each other. Okay. So because of these collisions, we get collisions of these conducting electrons with what? These electrons will collide with the vibrating ions of the crystal lattice. So these electrons, these free electrons will collide with the vibrating ions of the crystal lattice. Conducting in metals, the electrical resistance is due to collisions of vibrating ions with the conducting electrons. With the conducting electrons means these are the reason for the conduction. Okay, conducting electrons will collide with this vibrating ions of the lattice, the crystal lattice, which leads to electrical resistance in my conductor. Okay, there will be a collision between vibrating ions with the conducting electrons of my crystal lattice, which leads to electrical resistance here. Okay, students. So now in superconducting state, what is happening? Now it is in a metal normal state. Now what happens in the superconducting state here? What happens is these electrons scattered in pairs. Now these electrons are there, no? The conducting electrons, they'll be scattered in terms of pairs. They form pairs and they'll be scattered away. But there won't be an individual. So now what happens when they are traveling like pairs? There will be, how do they travel in pairs? They exchange some force between these electrons. Okay, they exchange some force between these two electrons and they form a pair. See here in Yukawa meson theory, in nuclear physics, what we have told, that every nucleon, this is proton or neutron, then they exchange pi mesons. That is the particle which is exchanged between the proton and neutron, or proton and proton, or neutron and neutron, such that they bind together and they form nucleus. Okay, such that they bind together and they form nucleus. Okay, so that's the reason. One second. They bind together and they form nucleus. Okay, students. They bind together and they form nucleus. So inside nucleus, what are the particles we have? Protons, neutrons. So protons are positively charged and neutrons are neutrally charged. But see, when a proton and proton come nearby, they have to get repelled, right? They have to get repelled and the nucleus should collapse. But why nucleus is stable? Stability of nucleus is explained by what are the forces called? Nuclear forces. So what is happening? Who is binding one proton with the other proton? That is the force. That means there is a particle is getting exchanged between this proton and this proton. What is that particle? Pi meson. Here pi is 0 meson. Okay, is exchanged between this proton and this proton, and hence which is making your nucleus stable. Okay, similarly here the electrons are moving in the form of pairs now. In superconducting state, I am talking about in superconducting state. In normal state, the electron is traveling individually and colliding with the lattice ions, vibrating lattice ions, and hence it is giving us what? And hence it is giving us current, electrical resistance in the conducting, with the conducting electrons. These conducting electrons will collide with the vibrating lattice ions and hence giving out the electrical resistance, right? But here these electrons are traveling as a pairs, means there is an exchange force between these two electrons. Okay, now when the electrons are having opposite spins and momenta, now if the electron is having this spin and this spin, opposite spin, they'll be attracted easily towards each other. Okay, there will be strong attractive force between them. So when in superconducting state, what is happening? Okay, this force of attraction is more, okay, than the electrostatic force of repulsion between this negative charge and negative charge. Okay, hence all the conducting electrons will become a bound system. They are bounded together. So all the electrons will become bounded together. Hence there is no collision with the lattice ions. Hence there is no collision with the lattice ions. They're bounded together, right? There is no exchange of energy from this bounded together electrons with the lattice ions. Now, when an electric field is applied externally, now we are going to apply an electric field externally uh, to a substance in superconducting state. Now, when my substance is in superconducting state, I am going to apply an electric field from outside, external electric field. Okay. Now what happens? These bounded electrons, paired electrons, will gain again more kinetic energy. They gain energy and they'll move with more kinetic energy, which gives rise to a current. Gives rise to a current, because electrons travel means we get current, right? Hence, these electrons will not get slowed down, but in addition, they'll get faster, and hence the resistivity will become zero. The resistivity gradually becomes zero. Electrical resistance will become zero. Hence, the resistance of superconductor becomes zero. Okay. This is the reason the superconducting resistance will become zero. Again, I'll explain you what is happening. See, when my metal is in normal state. So why metal has electrical resistance? Because here the conducting electrons will collide with the vibrating lattice ions inside the crystal lattice. Okay. Now what happens? Obviously, because of that, the energy of the electron will reduce, and hence they produce some resistance from these ions we have. So there is an electric resistance developed inside the metal when it is in normal state. Now, in superconducting state, what is happening here? Now there won't be, the resistance becomes zero in superconducting state. Why? What is happening? Now these electrons will exchange some force between them, and also if they are of opposite spins, they get attracted to each other rather than repelling from one another. They get attracted to each other and they form, they will become bounded to each other. They'll form bounded electrons. They bound together, and hence they won't exchange any energy with the lattice ions, vibrating lattice ions. Hence, what happens? Now the electrical resistance will not be becoming zero. Rather, when we apply some electric field, these electrons will move faster with higher kinetic energy, and they give more current. Okay, they give more current with full zero resistance. This is nothing but superconducting state. Okay, that is the reason we have superconducting state. Okay, so this is a concept of superconducting state, and because of zero resistance. Okay, let me explain you the effect of magnetic field on this in your next class. Okay, students, in your next class I will explain the effect of magnetic field on the superconducting material, and what happens to the critical temperature, or how it is related to the critical temperature, and how would it be related to the superconducting state. Okay, so today we have done, so what is superconductivity definition I have done, and basic experimental facts we have done, and superconductivity definition, experimental facts, superconductivity and zero resistance is very important. I have explained you the concept, right? Entirely comes under superconductivity. So tomorrow I'm going to explain, next class, effect of external, what is this field? Magnetic field I'm going to explain. So what happens if I apply some external magnetic field? That means there is the superconducting state is destroyed by applying external magnetic field. It can be retained to its, the superconductor can be made into a normal state, can be brought back to its normal state by applying some magnetic field. So how much magnetic field we have to apply? External magnetic field, Hc. So what is the critical magnetic field? Let us learn in the next class. Okay, students, thank you so much for your patient listening. Let me talk to you in the next class. Thank you so much.